one of these?
Yes.
Okay. Is this one working? Okay. Hello, everybody. Good evening. Thank you very much for having me here in the conference. So this is a research project that we have started. This is the first stage of the project, and then we expanded on that after this paper. So basically, these are the co-authors, my co-authors. We all belong to the computer science department, so we're not actually from the architecture or the built environment. However, we have some advice from there. So basically, what we're trying to do in this project is that we're trying to build a system that navigates IFC files and IFC data using LLMs, which is the catchword for everybody now. And we are using something called a Graph Rag, which is a technique for information retrieval. So I'll talk a little bit about IFC and what is Graph Rag, the problem of IFC parsing, the Graph Rag solution that we introduce, the key findings and results of the proof of concept, as well as the conclusions and future work. So IFC is the acronym for Industry Foundation Classes. This is a widely adopted standard for representing BIM, building information models. It has been introduced by Build Smart, and this was in 2020. Most BIM platforms are using IFC standards now as the primary format for storing data, exchanging information about buildings, architecture components. Anybody using IFC files in their daily life? Can you raise your hand if you use IFC files? Great. So you know what I mean when I say it is notoriously complex. Am I right? It is. Okay, so if the main concept of our system is that we turn the IFC data into a graph. So you know the entities and the elements in the IFC standard. If I tell you, for example, if you can guess how many nodes and edges for this simple bungalow, if I want to turn the IFC standard for this one into a graph, how many would I have if I have a graph for this house? Can you guess? Give me a wild guess. What do you think? 1,000, 2,000? What do you think? Okay, so we don't have enough time. We have a slide here, but I don't think it's going to work because this is not my laptop. So for this one, in order to turn the IFC entities and elements of this small house into a graph, we had about 47,000 nodes and 82,000 edges. You see how complicated the graph is. So the IFC standard is very important because it ensures interoperability. Different stakeholders can use it at the same time. However, there is a problem is that it is very difficult to navigate because of the deeply nested architecture of the IFC data. For example, if I'm talking about the IfcWall, I have to go through all this relationship. So this means it increases the cognitive and technical barriers, and it limits accessibility to non-technical stakeholders. For example, if I want to parse a BIM in IFC standard, I would not be able to do it unless I know these standards itself. There are lots of research in NLP, natural language processing, and LLM, in order to parse IFC in an intuitive manner. There's a significant improvement in research. You can go back to my paper in the literature review, have a lot of information extraction attempts using NLP with IFC files. However, we have what we call the flattening problem, which means that usually all the NLP research and AI research changes the IFC standard into another flat format, such as the JSON or tables, which means that it loses the relational context of the entities in the IFC. So we thought that it is limiting the reasoning capabilities when it comes to information retrieval. So we thought that we need something that has sort of a structure-aware querying, where we have the context, which is the relationship between the entities in the information retrieval. So we thought of trying Graph Rag. This is an information retrieval technique that we are using in natural language processing. We thought of using this. Basically, Graph Rag is utilizing something called Retrieval-Augmented Generation. I'm not sure if you know this concept, but basically we have a database. We do not rely basically on the pre-trained knowledge of the large language knowledge, we also add a database with that. So in order to reduce hallucination. So what happens in the graph rag is that we add, instead of giving just a database, we change the data into a graph. So we have in graph rag, the technique is combining the graph database with LLM querying. And the reasoning basically enables complex relational reasoning because it's not retrieving a flat data, but rather a graph. Oops. Okay, so this is the pipeline for our proof of concept system, which changes the IFC to graph. In order to change IFC into a graph, we treat the entities such as the IfcWall, the IFC door, etc., as the nodes, and the relationship between them are the edges. We experimented with two configurations, the holistic graph, where we have the whole building as an IFC graph, or the elements, and then a targeted graph where we have just one element, specifically which shows the IFC wall. So this graph shows the pipeline of how we start. The main idea of the system is that we want to have an intuitive interaction with the IFC standards. So for example, the user would ask a question like this one: what is the material of the second floor wall? And then it gets an intuitive natural language answer like the second floor wall material is beton. I will not get into the complications of the backend, but basically what we do in the graph rag is that we have the graph database of the IFC building, and then we have two enhancements for the LLM. The first one, what we call is a query enhancement, where we change this natural query by the input into something called the cipher query, which is a language known by a platform called Neo4j, where we use the graph rag technique. And then the knowledge enhancement is basically pulling from the pre-trained knowledge of the LLM itself. So both enhancements turn the input query into a cipher query that retrieves the information from the graph, and then the answer comes also in cipher language, and we change that by the LLM agent into a natural answer like this one. As opposed to the IFC parsers, this is one type of IFC parser. So our system is trying to do the same thing here. This one is called Blender. So this is I'm not sure if you know that. I'm sure you do that. So for example, if I want to answer this question, what is the dimension area of this wall in the building? As I said, this is not my field of expertise, but I know from the software that we have to go through different systems. We have to go to the IfcWall, and then into that we find the correct wall, and then step 3, we find the property that we're looking for. What we're doing is that we're just giving an answer in natural language. Okay, I'm going to show you a short video of our, hopefully I can do this. Okay, so let's have it in quick. As this in Chinese, I want to have it quicker. Okay, that's fine. I'm not sure if you can see, it's a little bit small, but this is the graph rag of a small house. And I choose a small house because you just ask, as I say, normal questions rather than having a software for the IFC parsing. We ask a question like, give me the names of the walls, give me the constraint of the walls, and then the LLM agent in the back end handles all the IFC jargon and gives you natural language. I can also change it into table format because I'm using all the capabilities of the LLMs, like that, for example. Also, sometimes I can ask what we call multi-hop questions. So, for example, not just asking about the thermal resistance of a wall, I can also ask about this one. What are the walls connected to this wall? So it gives me the walls connected to this wall, and a question such as, what is a wall that is connected to this wall that has a different material to that wall? And this is the strongest part of our system, is that we are asking multi-hop questions, not just simple questions. Okay, in my presentation, you can have the full video through this QR code if you want, but for sake of time, I will go a little bit faster. So that was the first experiment. We expanded, as I said, on that. It was 60 questions. We tried with 3 LLMs. The best performance was GPT-5, and we had an accuracy of 95% and F1 score of 0.97. Insights is that if we are trying to expand on this, the accuracy significantly reduces when it comes to the holistic graph when we are dealing with a whole building. However, we have a reliability in this system because we have minor true negatives. True negatives means that the information is not in the IFC data and the LLM says, I do not know, which means that it does not hallucinate. And it is intuitive for users, as I said, which is the main idea for our system. This is our building, the Steam House at BCU. And this is my LinkedIn, and this is my connection if you want to connect if you're interested in our work. We're still working on it, by the way. Thank you very much.
So, any question? Yes, Donald's hand was up first. He was first, sorry.
Hello, and thank you very much for the presentation. Really interesting.